Okay, so for the entrance question, I was asking you to first fill in the pi bonding molecular orbital diagram. Something I didn't actually mention in lecture was that molecular orbital bonding is used to describe our pi bonding. It also can be used to describe all the sigma bonding, which are usually lower in energy. So, but we're not looking at the sigma bonding molecular orbitals right now because our reactions we're interested in involve the pi bonds. They help us predict it, and they're much more complicated to come up. All right, so let me fill this guy in. I drew up the molecule above and I numbered it 1 to 6 around this way. I decided to go that way because there was a branch here, but you know what? This wouldn't be the correct nomenclature numbering because it should be 2 instead of 3. That's okay. But I numbered it that way, and I put the 6 through 5, meaning like carbon 6 with the p orbital, 5, 4, 3. Okay. And I got to remember my nodes. How many nodes does the lowest energy one have? 0, 1, 2, 3. And then my center symmetry, center symmetric, and then center anti-symmetric, center symmetric, center anti-symmetric. All right? And then I start shading things in with that info. With the other thing too, the other thing that's helpful is to start by just shading one side all the same. And it could be either side. In lecture I use this side, I'll just continue to use this side. And in lecture I shaded the bottom one on the bottom. I could shade the top and go top to top on this. So let's go down, the bottom, the bottom, the bottom. And then when I shade the other side, I go bottom, because it's in phase with the whole bottom. And then I go from bottom to top, I have to switch. Bottom, top. And when I did that, what do you think, Emily? Did I come up with still center symmetric, anti-symmetric, all that? Yeah, because my outer ones are symmetric, my outer ones are anti-symmetric. Symmetric, anti-symmetric. That followed that. And then I know the bottom one has 0 nodes, so I just fill it all the way in. No nodes, looks good. It's center symmetric. These are symmetric in the middle. The outer ones are symmetric. My next one, I need 1 node. So I'm going to need to fill in this one and that one, so it creates a node in the middle. So I have bonding, anti-bonding, bonding, 1 node, 1 node. Overall bond order of 1, minus 1, 0, plus bond order of 1, bond order of 1, 2, 3. Next one up, I need to go center symmetric. So I need 2 nodes. So I need to do the middle ones up and up. If I were to guess wrong on this, it's no big deal. Just erase it. So I have a node here and a node there. 1 bonding interaction. And is it center symmetric? Yes, symmetric, symmetric. The top one's easy. You just alternate. Bottom, top, bottom, top. And that should be giving me 3 nodes, and it does, as well as anti-symmetric, anti-symmetric. Okay, now I'll fill in my electrons. How many pi bonding electrons do I have, Bo?
Which one?
How many pi bonding electrons? 4. 4, huh? So I'll go initially ground state 1, 2, 3, 4. Then, is this reactions done? Oh, well, before that happens, this would be the highest occupied molecular orbital, and then this is the lowest unoccupied molecular orbital. That's what we have going now. If we shine light at this, of this energy, our configuration will look like this. Now here we have our singly occupied molecular orbital, our SOMO. Okay, that part of the problem. And then we want to use that to help us with this question. I'll work it out under the exit question here. Yeah.
How picky are you going to
I'm not worried about it at all.
Okay.
I'm not 100% sure.
Me neither.
I just know that that explains why I use that orbital for the electrocyclic.
So you don't care what the spin state is for the one?
Yeah. I'm not sure what is lowest in energy. I know when two electrons are in the same orbital, they have to have opposite spins. But that can be broken in a black hole. Electrons kind of the whole universe, the whole sun is collapsed on them. All right, so next up, we're gonna do this reaction. Let's start with just the regiochem. And on this one, I've got cis and cis, huh? So this is cis, this is cis. And then in order for this reaction to occur, this middle bond, which has some partial pi bonding, needs to have a particular stereochemistry. What does it need to have, Bree? It's that S one. S cis or S trans? Which one is it? Yeah, it has to be S cis, which I drew it up. S cis there. So it's S cis because it has a partial pi bond. S for sigma. Cis and trans. Okay, and then we're going to just figure out the regiochem first. Number it the same as I did up there. 1, 2, 3, 4, 5, 6, 7. And I'll have carbon 3 hinged. Swing down and make a bond between 3 and 6. And then hinge on 5. 5 bond will go between 5 and 4 because 4 lost the pi bond. Got it, right? And then Robert, where's my two stereocenters? Which carbons? Yeah. So this is my regiochem, but I also want to know the stereochem. Are those two groups going to be cis to each other, like both wedged or dashed, or are they going to be one wedge, one dash trans? The way I'll figure that out is I'll look at this. I'm going to start rotating it around. Just twisted it that way in the plane, and then I'm going to twist it so that it's coming out of the plane at us. And I'll add on the p orbitals that are on the end. And I'm going to shade those as needed according to our diagram and whether we're using heat or light. So yeah, we're using light on this one. So Yukaika, what is the shading I should use for these?
Shade one on the bottom and
So I'll make it just the same here. It's this molecular orbital 3 I'm using, huh? So it's going to be shaded on the bottom on this one. And then how do I shade this, bottom or top? Remember, light hit this, so that's the orbital that's going to determine. Shade on the bottom. Shade on the bottom. It's the outer carbons, right? Now, do you agree with me, Yukaika?
Yes.
Okay. And then, which way do you want to go with this, Yukaika? Clockwise or counterclockwise? Okay, left one, counterclockwise. Everyone's picked counterclockwise first today. It's counterclockwise culture we have here. All right, so when I do that, does my methyl go up or down? What do you think, Yukaika, this methyl? Up, yeah. And when I do this, does the p orbital dark phase go to the middle or the light phase?
Dark phase.
Dark phase. So which way do I have to rotate this p orbital to make sure dark phase meets with dark phase? Clockwise, huh? And when I do that, what happens to that isopropyl? Does it go up or down? Up. Okay, so now I know my product is going to be the product's going to be the one with the two groups cis to each other. And for this particular one, should I do them wedged or dashed? If I put the isopropyl here, I guess I'll do it this way. It's going to be wedged. Do you agree with that? Both going to go up. Like if I look at this guy, it's going to look like this. And if I brought it over, can you see it? Just in a little bit. So that's that enantiomer. I'm also going to get the other enantiomer. And they're not a meso this time because the methyl and the isopropyl was different. How did I get this one here? How did this get formed? Do you have a guess, Sarah?
You turn it the opposite.
Yeah, if instead of going dark phases in, I would have went clockwise here. I'd have to go counterclockwise there, and then my methyl would go down and my isopropyl would go down, and it would result in this one. And it's equally likely to go both ways, so you get a racemic mixture.